In December of 1941, the United States entered the Second World War carrying confidence, but not preparation. Its factories were vast, its population immense, yet the tools it brought to battle were often unfinished, untested, or inherited from a different era. The shock of Pearl Harbor forced America into a global war at full speed, but its military machinery had not yet caught up with the demands of modern combat. In the Philippines, American and Filipino forces fought with rifles short on ammunition, aircraft grounded by maintenance failures, and tanks too lightly armored to survive against determined Japanese assaults. In North Africa, U.S. troops faced German veterans hardened by years of war, equipped with refined tactics and weapons already proven across Europe. The early encounters were not merely defeats of strategy, they were exposures. America's equipment often failed at the moment it was needed most. On the ground, soldiers learned quickly that doctrine offered little comfort when radios broke, artillery missed its mark, or vehicles stalled in sand and mud. Improvisation became a survival skill. Crews welded scrap metal onto vehicles. Infantry adapted tactics meant for another war. Victory, when it came, was earned by flexibility rather than technological superiority. Abroad, observers took note. German analysts dismissed American weapons as crude and over-engineered. Japanese planners believed U.S. industry lacked focus, mistaking scale for speed, and assuming democracy moved too slowly to adapt under fire. To them, America looked powerful, but clumsy. Yet beneath the surface of these early failures, something quieter was beginning to take shape. Field reports mentioned unusual details: artillery shells detonating closer than expected, radios that held signal through chaos, vehicles reaching places maps said were impassable. None of it was dramatic. None of it made headlines. But again and again, small notes hinted at outsized effects. They were not wonder weapons. They were not symbols of national pride. They were solutions, practical, modest, almost invisible. And slowly, a different question began to surface within the chaos of retreat and recalibration. What if America's advantage was not in the size of its machines, but in the details no one was watching? Somewhere far from the front lines, engineers were already working on answers. From the moment America entered the war, a reassuring story took hold at home. Newspapers spoke of endless assembly lines, of tanks rolling out by the thousands, and aircraft filling the skies in silver formations. The nation imagined victory as an equation of volume: more steel, more engines, more firepower. If America could simply outproduce its enemies, the war would solve itself. But on the battlefield, that myth unraveled quickly. Early American tanks were often outgunned by German armor, their silhouettes tall, their guns underpowered. Fighters entering combat in 1942 struggled against opponents refined by years of experience. Even when numbers favored the United States, quality lagged behind ambition. Quantity, it turned out, did not automatically translate into dominance. Within headquarters and planning staffs, attention remained fixed on the visible symbols of power. Divisions were measured by how many tanks they fielded, air forces by how many aircraft they could launch. Little notice was paid to the smaller tools that connected these forces: the radios that failed under fire, the artillery fuses that detonated too early or too late, the logistical equipment that determined whether ammunition arrived on time or not at all. On the front lines, soldiers adapted in ways no manual had anticipated. Tank crews adjusted sights with chalk marks. Infantry learned to relay messages by shouted timing and intuition when communications failed. Mechanics cannibalized wrecked vehicles to keep others moving. These were not acts of innovation celebrated in communiques. They were quiet corrections to a system that had not yet learned what mattered. Still, the belief endured. Wars, it was said, were won by the biggest guns and the heaviest bombs. Everything else was secondary, supporting detail, not decisive force. And so the most consequential American inventions of the war passed largely unnoticed, hidden in crates, workshops, and test ranges far from the cameras. While the world watched the giants of war take shape, the tools that would truly shift the balance were being built by people few had ever heard of, and fewer still were listening to. The inventions that would reshape the American war effort did not emerge from grand strategy rooms or ceremonial laboratories. They came from small workshops, converted classrooms, and civilian factories still smelling of oil and machine grease. Across the country, engineers who had never worn a uniform were suddenly handed problems measured in lives. Their task was not to build symbols of power, but to fix what was failing at the front. Wartime necessity collapsed the distance between battlefield and blueprint. Reports returned from Guadalcanal, Tunisia, and the skies over Europe, carrying blunt assessments written in grease pencil and fatigue. A radio failed under rain. A shell detonated too late. A vehicle could not cross water where the map said it should. These notes did not move through layers of ceremony. They landed directly on workbenches, and weeks later, sometimes days, new prototypes followed them back into combat. The people solving these problems rarely resembled the generals whose decisions filled history books. They were machinists adjusting tolerances by feel, chemists refining compounds that burned more predictably, mathematicians translating motion and probability into metal and glass. Their authority came not from rank, but from whether their ideas worked when tested by gunfire. None of what they produced looked impressive at first glance. There were no sweeping silhouettes, no dramatic photographs for newspapers, yet these modest tools multiplied the effectiveness of everything around them. A gun did not need to be larger if its shell detonated at the right moment. An infantry unit did not need more men if it could communicate instantly. Power, they discovered, could be amplified without being obvious. Slowly, a realization spread through the engineering community and then outward. Victory might not hinge on a single decisive weapon, but on dozens of small corrections made relentlessly, quietly, and at scale. The war was becoming a system, and systems rewarded precision over spectacle. By 1942, the U.S. military began to pay attention. Commanders who once dismissed civilian ideas as impractical started requesting them by name. Testing units expanded. Budgets shifted. The door between laboratory and battlefield, once barely open, swung wider with every successful trial. And among these uncelebrated projects, one invention stood poised to redefine how death fell from the sky, unseen, calculated, and impossible to ignore. In the early years of the war, anti-aircraft fire was an exercise in frustration. Crews aimed carefully, calculated altitude and speed, and watched shells burst uselessly in empty sky. A fraction of a second too soon or too late rendered tons of steel meaningless. Against fast-moving aircraft, especially in poor visibility, even well-trained gunners were often reduced to hoping rather than hitting. To solve the problem, a small group of scientists proposed something that bordered on the absurd. They suggested placing a miniature radar set inside an artillery shell, an electronic eye that would sense when it was close to an aircraft and detonate automatically. The idea promised to remove human timing from the equation entirely. It also sounded impossible. Commanders and procurement officers reacted with skepticism. Electronics were delicate. Artillery shells were not. The notion that vacuum tubes could survive the shock of being fired from a gun at thousands of feet per second seemed naive at best. Even if it worked once, how could it ever be manufactured by the millions, shipped across oceans, and trusted in combat? Testing changed the conversation. On controlled ranges, shells fitted with the new proximity fuse exploded with unnerving precision. Targets that had previously slipped through defensive fire were suddenly shredded by near misses. The sky itself seemed to turn hostile. What mattered was no longer direct impact, but proximity, mathematics replacing guesswork. By late 1943, the fuse entered combat. Anti-aircraft units reported kill rates several times higher than before. Aircraft formations broke apart. Pilots learned that evasive maneuvers once considered safe now led directly into invisible envelopes of detonation. The weapon did not announce itself. It simply worked. Its impact became unmistakable in the Pacific. As Japanese pilots turned to kamikaze attacks, proximity-fused shells detonated in lethal halos around incoming aircraft. Planes were destroyed before they could reach their targets. Crews never saw what hit them, only sudden light, then nothing at all. An invention once dismissed as too complex had become brutally reliable. The proximity fuse did not change the size of guns or the number of ships at sea. It changed timing. It changed probability, and in doing so, it quietly rewrote the balance between attacker and defender. By the war's final year, the fuse was everywhere, embedded in artillery, naval guns, and air defenses across the globe. Few outside technical circles understood how it worked. Fewer still knew who had built it. But in workshops and proving grounds across America, engineers were already applying the same philosophy elsewhere, finding other places where precision, not power, would decide who survived the next engagement. In November 1943, at the coral atoll of Tarawa, American planners encountered a reality their maps had failed to capture. Landing craft grounded hundreds of yards from shore, stopped cold by a reef invisible at high tide. Marines waded forward through waist-deep water under machine gun fire, burdened by rifles, radios, and fear. The assault stalled not because of enemy strength alone, but because the sea itself had become an obstacle. The solution had existed for years, largely ignored. Originally designed as a civilian rescue vehicle for swamps and floodplains, the landing vehicle tracked, known to its crews as the Alligator, was slow, ungainly, and mechanically suspect. Its armor was thin, its silhouette awkward. Many officers dismissed it as a curiosity unsuited for combat. Trials began quietly. On beaches and marshes, the LVT crept from water to land without hesitation, its tracks biting where propellers failed. Critics noted its vulnerability and limited speed. Engineers listened, not to defend the design, but to change it. Steel plating was added. Ramps replaced high sides. Capacity increased. The vehicle evolved not through theory, but through repetition. When the LVT returned to combat, the difference was immediate. At island after island, it crossed reefs, surf, and sand in a single motion, carrying troops, ammunition, and even light artillery directly onto hostile shores. Where boats forced men into exposed marches, the LVT delivered them forward and intact. The sea no longer dictated the terms of the assault. Japanese defenders, trained to concentrate fire on predictable landing zones, found themselves disoriented. Attacks came from angles they had believed inaccessible. Defensive plans, carefully rehearsed, unraveled as American units appeared where no landing was supposed to be possible. Mobility had rewritten the geometry of battle. The LVT never became a symbol of power. It was too slow for glory, too inelegant for posters. Yet it solved a problem that had killed thousands. It turned logistics, movement, timing, access into a form of offense. The Pacific War, defined by distance and water, began to bend in America's favor. By 1944, amphibious doctrine itself had changed. Beaches were no longer barriers, only transitions. And as engineers continued refining the vehicles that carried men ashore, another quiet truth became clear. In modern war, movement was no longer just about speed. It was about going where the enemy believed you could not. For much of the early war, communication remained bound to older habits. German and Japanese units relied heavily on field telephones strung across fragile lines or on runners moving through shellfire with memorized orders. When wires were cut or messengers failed to return, units fought in isolation, guided by assumptions rather than information. American forces began the war with a different, still unproven idea. Lightweight radios, awkward, battery-hungry, and often temperamental, were issued down to the lowest levels of command. The SCR-536, small enough to carry by hand, and the larger backpack-mounted SCR-300 promised something new, voices moving through the chaos of battle, untethered to wires or fixed positions. Skepticism followed them into combat. Officers worried about limited range and reliability. Infantrymen cursed weak batteries and static-filled signals. Critics argued that such devices could never replace disciplined runners or established lines. The radios, they said, were too delicate for war. Combat answered the question. In jungles, deserts, and ruined cities, radios did not eliminate confusion, but they shortened it. A platoon pinned down could call for support in minutes rather than hours. Artillery adjusted fire in real time, shells walking closer with each correction. Tanks and infantry learned to move together, sharing sight and sound instead of guesswork. The effect was cumulative. Units began to behave less like independent fragments and more like coordinated systems. Orders changed mid-action. Opportunities were exploited before they vanished. Where earlier wars demanded rigid plans, radio-equipped forces adapted continuously, turning speed of communication into tactical advantage. Enemy observers noticed. Japanese reports described American units advancing with an unsettling unity, as if guided by a single will. German veterans remarked on the rapid concentration of firepower that followed even small engagements. What they faced was not simply better equipment, but a different rhythm of war. The radios did not fire shots or breach defenses. They did something subtler. They compressed time. They allowed decisions to travel faster than fear. In doing so, they transformed chaos into coordination and coordination into momentum. By 1944, the radio network had become invisible, so embedded in operations that it was no longer remarked upon. Yet it underpinned every advance, every combined assault, every rapid response. And as engineers looked at what communication and timing could achieve, others were applying the same logic to metal, motion, and mathematics, preparing the next T shift that would reshape the front lines. By the time American armored units reached Western Europe, a quiet anxiety followed every Sherman tank into battle. Against German Panthers and Tigers, the Sherman's early guns often felt inadequate, its shells striking enemy armor only to glance away or shatter harmlessly. Crews learned to maneuver for flank shots, to close distance under fire, or to rely on numbers and air support. Courage compensated where physics did not. German armor had been built around a simple assumption that protection would outpace penetration. Thick frontal plates, sloped steel, and long-barreled guns gave German crews confidence in head-on engagements. On paper, they were right. The standard American 75 and even early 76 rounds struggled to defeat that protection except at dangerously close range. The response did not come in the form of a larger gun. Instead, American scientists turned inward to the mathematics of mass, velocity, and energy transfer. They designed a new kind of projectile high-velocity armor-piercing. Its secret was density. A small core of tungsten, far heavier than steel, sat inside a lighter shell. When fired, it traveled faster, struck harder, and concentrated its force into a smaller point. The concept was elegant. The challenge was everything else. Tungsten was scarce, demanded by machine tools, aircraft engines, and industry itself. Manufacturing tolerances were unforgiving. A slight imperfection meant failure at the moment of impact. Many questioned whether such rounds could ever be produced in meaningful numbers, let alone supplied to frontline units already strained by logistics. Testing shifted opinion. On proving grounds, HVAP rounds punched through armor that had resisted every previous attempt. Penetration tables changed. Engagement ranges doubled. What had once been theoretical became measurable, repeatable, and undeniable. When HVAP reached combat units in late 1944, the effect was immediate. Sherman crews reported penetrations against Panthers at distances previously considered suicidal. German tank commanders, accustomed to frontal immunity, found their confidence shaken. Armor that had once guaranteed survival no longer did. The rules of engagement changed without announcement. The shock was mutual. American crews, long trained to think defensively, began to engage with new assurance. The Sherman had not become invincible, but it had become credible. With HVAP, the 76 gun transformed from a limitation into an equalizer. Victory no longer depended solely on positioning or luck. It could be calculated. German reports reflected confusion. Tanks were destroyed from angles and distances that contradicted established doctrine. Investigations followed, searching for larger guns or new tactics, but the answer was smaller, denser, and already in circulation. The battlefield had shifted beneath their feet. HVAP did not replace existing ammunition. Supplies were limited, and rounds were reserved for moments that mattered most. But in those moments, the difference was decisive. A single shot could change an engagement. A single engagement could open a road. The round never became famous. It lacked the drama of new tanks or breakthrough offensives. Yet it embodied the American approach taking shape by 1944, solving problems not by escalation, but by refinement. As HVAP quietly altered armored combat, it became clear that the front line was being reshaped by a series of such adjustments. None decisive alone, all overwhelming together. And elsewhere, other overlooked machines were already preparing to change how armies moved, supplied, and survived under fire. Few wartime machines inspired less confidence at first sight than the Duck. With its boat-shaped hull mounted on truck wheels, it looked neither seaworthy nor roadworthy, a compromise that satisfied no one. Soldiers mocked it openly, calling it an ugly duck, a contraption better suited for parades than battle. Even senior commanders questioned its purpose in a war already crowded with specialized vehicles. Dwight D. Eisenhower was among the skeptics. Amphibious trucks, he believed, solved a problem that did not truly exist. Beaches could be crossed by landing craft. Rivers could be bridged. Logistics, in theory, would follow traditional paths once a foothold was secured. The Duck appeared redundant, another strain on production lines already pushed to their limits. Combat dismantled those assumptions. When the Duck was finally used at scale, it revealed a capability no single-purpose vehicle could match. It could drive from a depot, enter the water without pause, and emerge onto hostile shore still carrying its load. Artillery pieces, ammunition crates, fuel drums, and wounded men moved seamlessly across boundaries that had once forced complex transfers. At Normandy, the value of the Duck became unmistakable. The beaches were not simply assault zones, they were supply bottlenecks. Tides, weather, and wreckage disrupted unloading schedules. The Duck ignored those constraints. It ferried supplies directly from ships offshore to units inland, keeping momentum alive when delays might have stalled the invasion. What mattered was not speed, but continuity. As the campaign moved inland, rivers replaced beaches as obstacles. The Duck adapted without modification. At the Seine and later at the Rhine, amphibious trucks carried men and materiel across wide, fast-moving water while bridges were still under construction or under fire. Entire divisions crossed using vehicles that had once been ridiculed as impractical. German intelligence failed to grasp their significance. Reports dismissed the Duck as a civilian utility vehicle, unsuitable for serious military use. This misjudgment carried consequences. German defenses planned around destroyed bridges and flooded terrain found themselves outflanked by supply lines that simply flowed around obstacles rather than confronting them. The Duck never led an assault. It never appeared in victory photographs. Yet without it, advances would have slowed, pauses would have lengthened, and opportunities would have closed. It did not fight the enemy directly. It defeated geography. In this way, the amphibious truck embodied a deeper shift in American warfare. Logistics was no longer a background function. It was an active force, shaping where and when battles could be fought. The unglamorous vehicle became a quiet conqueror of Europe's rivers and shores. As the Allies pushed forward, another unassuming invention was already transforming a different dimension of combat, one measured not in miles or tons, but in fractions of a second, and fought under the cover of darkness. Early in the air war over the Pacific, American pilots faced a persistent problem that courage alone could not solve. Aerial combat demanded deflection shooting, firing not at where an enemy aircraft was, but where it would be moments later. In the chaos of twisting dogfights, even experienced pilots struggled. Ammunition vanished into open sky, and victories often depended more on proximity than precision. Engineers approached the problem without romance. They treated aerial combat as motion and probability. By mounting a gyroscope inside the gun sight, they created a device that sensed angular movement and predicted lead automatically. The reticle no longer stayed fixed. It moved, calculating the point of interception before the pilot consciously could. The sight did not replace judgment, it augmented it. Skepticism followed. Many pilots distrusted a reticle that drifted across the glass, fearing it would distract at the moment of decision. Others doubted the complexity could survive vibration, altitude, and combat stress. The gunsight looked like an answer in search of a problem or a luxury for pilots who lacked instinct. Combat resolved the argument. When the gyro gunsight entered service on aircraft like the F-4U Corsair and the P-51 Mustang, hit rates increased dramatically. Pilots who had once fired long bursts learned to fire short, deliberate shots. Engagements ended faster. Survivability improved. The sky grew more unforgiving. Japanese pilots noticed the change almost immediately. Aircraft were struck at angles that defied expectation during high-speed turns from positions once considered safe. Maneuvers that had worked against earlier opponents now invited sudden destruction. What they faced was not superior reflexes, but superior calculation. The transformation was subtle but decisive. Air combat began to resemble an equation rather than a duel. Skill still mattered, but it was now reinforced by instrumentation. The pilot and machine operated as a single system, each compensating for the other's limits. The gunsight never announced itself. There were no visible flashes of innovation, no radical changes in aircraft design, yet it altered outcomes shot by shot, engagement by engagement. Air superiority was not seized in a single battle, it accumulated. By 1944, the gyro gunsight had become standard equipment. New pilots trained with it from the start, learning to trust the mathematics embedded in glass and steel. The future of aerial combat had arrived quietly, without fanfare. And as these small inventions, gunsights, radios, vehicles, munitions, began working together, their combined effect became impossible to ignore. The war was about to change not through one breakthrough, but through the convergence of many. By 1944, the American way of war had changed, not through proclamation, but through practice. On battlefields stretching from Normandy to the Marianas, U.S. forces moved with a speed and coordination that had been absent only 2 years earlier. Artillery responded almost as soon as targets were identified. Armor advanced in step with infantry. Aircraft arrived not by chance, but by call. What once felt improvised now appeared deliberate. This coordination did not come from a single invention. It emerged from integration. Radios carried requests forward and corrections back. Proximity fuses turned defensive fire into a protective envelope. Amphibious vehicles delivered supplies without pause. Specialized ammunition altered engagement distances. Each tool solved a narrow problem. Together, they formed a system. For German and Japanese units, the contrast was stark. They fought with discipline and courage, often to the last position, but their battles were increasingly isolated. Orders arrived late or not at all. Reinforcements moved along predictable routes. Firepower, when committed, could not be redirected quickly. The war they were fighting rewarded preparation and resolve. The war they now faced punished delay. American operational tempo increased quietly, almost invisibly. Attacks followed one another before defenses could reset. Breakthroughs were exploited instead of consolidated. A position lost at dawn could become a collapsed sector by nightfall. The battlefield no longer paused between decisions. This tempo was not mechanical. It was human, amplified by technology. Soldiers trusted that support would come when called. Pilots knew their fire would be more effective. Tank crews engaged with greater confidence. The tools did not replace courage, they multiplied it. What changed most was time. Decision cycles shortened. Observation led to action with fewer steps in between. The enemy still resisted fiercely, but resistance was met with coordination rather than reaction. Firepower arrived not in mass alone, but in sequence: artillery to suppress, armor to breach, infantry to hold, aircraft to isolate. None of this was visible from afar. There were no new silhouettes on the horizon, no sudden leaps in destructive power. The advantage lay in alignment. Small technologies spoke to one another through doctrine and habit. The battlefield became legible to those who could read it. By late 1944, the Allies were no longer responding to enemy initiatives. They were setting them. German counterattacks, even when tactically brilliant, arrived into environments already prepared to absorb them. Japanese defenses, meticulously constructed, were bypassed, isolated, and reduced methodically. the rhythm of war had shifted. This shift did not make victory easy. Losses remained heavy. Weather, terrain, and human error still intervened, but the direction was clear. The Allies dictated when and where battles occurred. They chose the pace, and the enemy was forced to keep up or be overtaken. Invisible technology had become strategy, not as theory, but as habit, not as doctrine alone, but as muscle memory built across thousands of units. The accumulation of overlooked inventions had produced something greater than any of its parts. And as this system gained momentum, it fed on itself, each success reinforcing the next, each advance accelerating the one that followed. What began as quiet innovation was now becoming something far more dangerous: inevitability. Innovation alone did not win the war. What made American technology decisive was not just invention, but repetition, its ability to be built again and again, unchanged, thousands of miles from where it was first imagined. Small breakthroughs meant little if they remained rare. America ensured they did not. Across the United States, factories adjusted with deliberate speed. Assembly lines were retooled to produce proximity fuses by the millions, radios by the crate, specialized ammunition by the trainload. Precision became routine. Variability was engineered out. What had once been experimental became standardized, reliable, and replaceable. This industrial discipline extended far beyond weapons. Supply chains carried spare parts, batteries, fuel, and repair kits across oceans and continents. Radios failed, but replacements arrived. Tanks were damaged, but recovered, repaired, and returned to service within hours or days. Aircraft landed with holes in their wings and flew again the next morning. The tempo established at the front was sustained by an invisible flow behind it. For American forces, this reliability reshaped expectations. Equipment was no longer hoarded as irreplaceable. Commanders planned knowing losses could be absorbed. Units trained on the assumption that broken machines would be fixed and that new ones would arrive on schedule. Confidence extended beyond morale. It was logistical. Axis powers faced a different reality. German industry, increasingly fragmented by bombing and resource shortages, struggled to maintain consistency. Advanced weapons existed, but in limited numbers, often requiring specialized parts that could not be replaced in the field. Japan, stretched across vast distances, fought with equipment that could not be replenished at the rate it was consumed. When something failed, it often failed permanently. The contrast grew sharper as the war progressed. American forces rotated units, refitted divisions, and integrated new technologies without halting operations. The machine did not pause, it adapted while moving. This capacity transformed logistics into a strategic weapon. Supply lines were not just sustaining forces, they were enabling new forms of warfare. Rapid advances became possible because fuel followed armor. Extended operations continued because ammunition never quite ran out. Flexibility at the front was anchored in predictability at the rear. By 1944, the American war effort resembled an organism more than an army, responsive, resilient, and self-correcting. Losses were absorbed not with desperation, but with process. The system learned, adjusted, and continued. In this environment, technology ceased to be an accessory to strategy. It became strategy itself. The war was fought as much in factories, ports, and repair depots as on beaches and hillsides. Victory depended on whether a nation could sustain complexity under pressure. The answer was becoming clear. The American machine of logistics was not elegant, but it was relentless. And as it rolled forward, it carried with it the weight of inevitability. Yet even as success approached, the cost of this system, measured in human lives and silent sacrifices, was still being paid, often far from the spotlight. By the final year of the war, American victory no longer arrived as a singular moment of revelation. It emerged instead as repetition, across islands, coastlines, forests, and skies, each battle shaped by tools so familiar they were almost invisible. Marines went ashore with radios slung over their shoulders and ammunition stacked inside tracked vehicles that crossed reef and surf without pause. Assaults still met resistance. still cost lives, but they unfolded with a coherence that had been absent at the war's beginning. In the Pacific, island after island followed the same grim rhythm. LVTs delivered troops directly onto hostile beaches, bypassing the killing zones that had once consumed entire waves. Radio traffic stitched scattered units into a single advance, artillery responding not by schedule, but by need. The jungle remained unforgiving, but American forces no longer moved blindly within it. In Europe, armored combat reflected a similar quiet transformation. Sherman crews still faced Panthers and Tigers with respect, but no longer with resignation. HVAP rounds were rationed carefully, saved for moments that mattered. When used, they altered engagements instantly. A frontal shot that once would have failed now punched through. A stalled advance resumed. A road, a bridge, or a village fell hours earlier than expected. Above these battles, bomber crews flew through skies that had grown subtly hostile to defenders. Anti-aircraft fire guided by proximity fuses filled space rather than aiming at points, forcing enemy aircraft away before they could strike. Fighters escorting the bombers operated with a new confidence. Gyro gunsights translated speed and angle into calculation, turning fleeting opportunities into decisive hits. Air superiority was not seized in a single clash, it accumulated, mission by mission. None of these inventions dominated headlines. Newspapers printed photographs of generals, ships, and surrendered cities. The tools that made those moments possible were rarely named. A fuse was too small to symbolize victory, a radio too ordinary, a tracked vehicle too awkward, yet they were present everywhere, shaping outcomes without demanding attention. Together, they changed the nature of effort. Soldiers still endured fear, exhaustion, and loss. Technology did not spare them from sacrifice. What it did was ensure that sacrifice was not squandered. Attacks were supported. Gains were reinforced. Success was followed by consolidation rather than collapse. The enemy felt the pressure even when they could not name its source. German units fought skillfully but found themselves outpaced, outcoordinated, and outsupplied. Japanese defenders resisted with determination, yet discovered that geography no longer protected them. Each battle felt less like an isolated contest and more like resistance against a system already in motion. Victory, when it arrived, appeared almost sudden. Fronts collapsed. Advances accelerated. Surrenders followed one another in quick succession. To those watching from afar, it seemed as though American power had simply overwhelmed its enemies by scale alone. But scale was only the surface. Beneath it lay years of refinement, thousands of small decisions made by engineers, logisticians, and soldiers adapting under fire. The war had been won not by a single decisive invention, but by the accumulation of many modest ones, each correcting a weakness, each narrowing the margin for failure. What was gained was clear: momentum, coordination, and ultimately, victory. What was lost was harder to measure. The war that rewarded precision did not reduce its cost. It only ensured that cost achieved its purpose. As the guns fell silent, the tools that had shaped every battlefield began to fade into storage depots and memory. Their legacy remained quiet, foundational, and easily overlooked. And with it came a final question that history would wrestle with long after the war was won. What price is paid when success depends on perfecting the machinery of war? Every successful invention of the war carried a shadow, rarely acknowledged and even more rarely recorded. Before a radio could be trusted in combat, it failed in rain and jungle heat. Before a fuse detonated with precision, it misfired. Before a vehicle crossed reefs or rivers reliably, it broke down under fire. These failures were not abstract. They were paid for in lives. Thousands died testing ideas that had never been proven in battle. Pilots flew with new gun sights while still learning to trust them. Tank crews loaded unfamiliar ammunition whose behavior they understood only in theory. Infantry carried radios that might work or might go silent at the moment they were needed most. Wartime innovation did not pause combat. It unfolded inside it. Engineers understood this burden with unsettling clarity. Each design choice carried moral weight. A miscalculation meant more than inefficiency, it meant death. Laboratories worked with urgency not because of deadlines, but because every delay prolonged exposure to failure at the front. Success saved lives, failure multiplied loss. There was no neutral outcome. For the men who used these tools, trust was often provisional. Soldiers relied on equipment they had not designed, could not repair under fire, and barely understood. A radio was a promise. A shell was a gamble. A vehicle was faith made of steel. They learned quickly which tools could be relied upon and which could not, sometimes at terrible cost. The war did not merely industrialize weapons, it industrialized sacrifice. Training accidents increased as machines grew more complex. Test pilots vanished without ceremony. Crews died proving tolerances and stress limits that would later be written into manuals. Many of the most important lessons were learned only once. After the war, credit followed success. Inventions were named, catalogued, and celebrated. Their impact was measured in victories and doctrines, but the men who refined them through trial and error often left no trace beyond service records and unmarked grave. Innovation remembered its triumphs more readily than its casualties. Memory softened the story. Progress appeared clean in hindsight, linear and inevitable. The hesitation, the fear, the lives lost between prototype and perfection faded from view. The tools survived. The cost did not. This forgetting was not deliberate. It was structural. History prefers outcomes to processes, victories to experiments. Yet without acknowledging what was lost, the story of innovation becomes incomplete, dangerously so. The quiet inventions that reshaped the war did not emerge fully formed. They were carved out of uncertainty by men who accepted risk they could not fully control. Their legacy lived on in effectiveness, reliability, and doctrine, but rarely in name. As the world moved into peace, these technologies evolved, refined further without the same immediacy of death. Their origins blurred into broader narratives of progress and power. The war ended. The accounting did not. What remained was a foundation built from small things and from the lives spent proving they worked. And in the years that followed, those small tools would shape a very different world, long after the men who tested them were gone. When the war ended, its machines did not disappear. They changed purpose, changed scale, and changed names, but their logic endured. The small inventions that had quietly shaped victory did not remain artifacts of a single conflict. They became foundations. Radios were among the first to evolve. What had begun as fragile battlefield tools matured into robust communication networks spanning continents. The lessons of redundancy, encryption, and decentralized command flowed directly into Cold War doctrine. Armies no longer imagined command as something fixed to headquarters. It became mobile, distributed, and continuous. Voices that once crossed beaches and jungles now crossed hemispheres. Ballistics followed a similar path. The tungsten core logic of HVAP did not end with the war's final tank duel. It reappeared in new forms, armor-piercing discarding sabot rounds, fin-stabilized penetrators, and kinetic energy weapons designed around velocity rather than explosive force. The idea endured. Penetration was a problem of physics, not size. Modern armored warfare inherited that equation whole. In the air, the gyro gunsight proved prophetic. Its principle, that machines could predict motion faster than human instinct, reshaped combat aviation. The moving reticle gave way to radar-assisted targeting, then to guided missiles. Pilots remained central, but the burden of calculation shifted steadily to instruments. What had once helped a pilot aim became the logic behind weapons that no longer required visual contact at all. Amphibious warfare. R2 carried forward its quiet revolution. The LVT's ability to cross sea and land without pause became doctrine rather than exception. Post-war amphibious vehicles grew faster, stronger, and more protected, but their purpose remained unchanged. Beaches were no longer endpoints. They were merely transitions. Modern expeditionary warfare still reflects that assumption. Even the proximity fuse left a long shadow. Its core idea, sensing position and triggering response automatically, echoed through air defense systems, radar-guided munitions, and eventually ballistic missile defense. The fuse had taught militaries to think in envelopes rather than points, probabilities rather than precision alone. That way of thinking now underpins entire defensive architectures. None of these evolutions occurred in isolation. Together, they formed the backbone of modern militaries, networks instead of hierarchies, systems instead of single weapons. The war had revealed that effectiveness emerged from integration, not spectacle. That lesson survived intact. What changed was visibility. In peacetime, these technologies were presented as progress, innovation, and deterrence. Their origins in desperate improvisation faded. The urgency that had driven their creation softened into routine development cycles and budgets. The memory of why they mattered grew abstract. Yet the lineage remained unbroken. Modern forces still rely on rapid communication, predictive targeting, mobility across terrain, and precision over brute force. The same small ideas, perfected under fire, continue to shape how wars are planned, fought, and imagined. The Second World War is often remembered for its giants, massive armies, towering machines, and decisive explosions. But what endured most completely were the quieter tools, the ones designed to solve narrow problems and ended up reshaping everything around them. They survived because they worked, and because they revealed something enduring about modern conflict. That advantage rarely announces itself. As the world moved forward, these small inventions receded into the background of military life, assumed rather than examined. And in that forgetting, the war's final lesson waited, ready to be rediscovered. Wars are remembered for their giants, tanks rumbling across borders, carriers cutting through oceans, bombs falling with names that echo through history. These are the images that endure, heavy with spectacle and scale. They offer clarity, power made visible, victory rendered in steel and flame. But that clarity is incomplete. Beneath the weight of those symbols lay a quieter reality. The war was shaped not only by what could be seen, but by what rarely was. Small tools, modest ideas, incremental refinements, these were the instruments that determined whether courage succeeded or failed. They did not replace heroism. They decided whether heroism had a chance. The equipment soldiers carried altered the meaning of bravery itself. Courage was no longer only the act of advancing under fire. It became the decision to trust a radio that might work, a vehicle that might reach shore, a shell calculated to detonate at precisely the right moment. Faith shifted from instinct alone to systems built by unseen hands. These technologies reshaped strategy by reshaping survival. A unit that could communicate did not need to fight blindly. A tank that could penetrate enemy armor did not need to rely solely on numbers. A pilot guided by calculation did not need to depend entirely on reflex. Small advantages accumulated until they were no longer small. This was not a victory of size. It was a victory of attention, of noticing what failed and refusing to accept it, of engineers who treated fractions of seconds, inches of armor, and miles of supply line as matters of life and death, because they were. America did not win the war through a single decisive invention or overwhelming brilliance revealed all at once. It won through persistence in the margins, through the steady accumulation of overlooked brilliance, repeated until it became decisive. The power lay not in any one machine, but in how many small machines worked together, reliably, relentlessly. History often prefers simplicity. It favors grand causes and singular moments. But the truth of modern war is more complex and more sobering. Victory emerges from systems built patiently, tested painfully, and trusted imperfectly by those whose lives depend on them. The true legacy of the war does not rest only in monuments or museums. It lives in doctrines, assumptions, and tools still in use, descendants of ideas born under fire, refined under pressure, and carried forward quietly into the present. Millions depended on inventions they never questioned and names they never knew. That dependence was not weakness. It was adaptation. It was the recognition that survival in industrial war required more than courage alone. In remembering only the giants, something essential is lost. War's deepest lesson is not about scale, but about consequence. about how small decisions made far from the front can shape the fate of those who stand there. In a war defined by giants, it was the smallest innovations that changed everything.